All right, so get this. So we're diving into a scenario where a star, like way bigger than our sun, reaches the end of its life, but instead of a dazzling supernova, it just vanishes.
It's like a cosmic magic trick.
Right. Like, where did it go? And that's the mystery we're unpacking today.
Yeah.
Based on excerpts from this fascinating paper, Constraints on Neutrino Kicks from Black Hole Binary VFTS 243.
Wow.
It's all about whether black holes can really form without the fireworks show we usually expect.
Yeah, it's certainly a head-scratcher. You'd think something as massive as a star collapsing would be anything but quiet.
Right. You'd expect a huge explosion.
For sure.
So where do we even begin with this?
Well, the story starts with VFTS 243, which is a binary star system in the Large Magellanic Cloud.
Okay.
A galaxy pretty close to our own.
Gotcha.
One star is a giant, about 25 times the mass of our sun, and its companion is a black hole, about 10 times the sun's mass. What's strange is this black hole seems to have formed without any sign of a supernova.
Okay, so we've got this giant star and a black hole buddy. But how do we know the black hole formed without a supernova? Isn't that kind of hard to miss?
You'd think so, but here's the thing. When massive stars typically go supernova, the explosion isn't perfectly symmetrical.
Okay.
It's like a lopsided rocket launch, giving the newly formed black hole a powerful kick in a random direction.
So like a cosmic pinball.
Exactly. But in the case of the VFTS 243, there's no sign of that kick. The black hole's companion star is orbiting peacefully, like nothing dramatic ever happened.
That's our first clue. Then the missing kick suggests something unusual happened during the black hole's formation.
Yeah.
And that leads us to disappearing stars.
Precisely. It's a theory suggesting that some stars might collapse directly into black holes without any visible explosion. The energy is carried away not by light and shock waves, but by these tiny ghostly particles called neutrinos.
Neutrinos. Aren't those the particles that are like notoriously hard to detect? They can pass through almost anything.
You got it. They're incredibly elusive, interacting so weakly with matter that trillions of them pass through you every second without you even noticing. But crucially, they do carry energy. Lots of it.
So instead of a huge, explosive supernova, we have this quiet collapse where the energy essentially leaks away as neutrinos.
That's the idea, and VFTS 243 is giving scientists a chance to test this theory in a real-world scenario. They're using sophisticated computer models to simulate a star collapsing directly into a black hole, and they're looking at what that would do to the companion star's orbit.
So they're basically running simulations to see if the disappearing star theory matches what we actually observe in VFTS 243.
Exactly, and here's the kicker. The models only match the observations if the black hole formed through a quiet collapse, with most of the energy being carried away by those ghostly neutrinos.
Wait, so this isn't just theoretical anymore. We have actual evidence that black holes can form without supernovae.
That's what makes this research so compelling. It challenges a long-held assumption and suggests there might be a whole population of black holes out there that we've been missing because they formed quietly. Not with a bang, but with a sort of cosmic whisper.
Hold on, if we've been wrong about how some black holes form, that means there could be way more of them out there than we thought, right? Black holes hiding in plain sight because they didn't announce themselves with a supernova.
That's a very real possibility, and that leads to a whole new set of questions about the evolution of galaxies, the distribution of matter throughout the universe. It really changes our picture of the cosmos.
Okay, this is officially getting mind-bending. But before we get too deep into the implications of all this, I want to go back to those neutrinos for a second. They seem to be the key to this whole disappearing star theory.
Yeah.
What can you tell us about them?
Well, for starters, neutrinos are actually much more complex than people realize. There are different types.
Wait, different types of neutrinos. I thought a neutrino was a neutrino.
There's actually 3 types or flavors, as physicists call them: electron neutrinos, muon neutrinos, and tau neutrinos. They each have slightly different properties and play distinct roles in the universe.
Okay, so this is where my brain starts to melt a little bit.
Sure.
3 flavors. What does that even mean?
It gets into some pretty complex particle physics, but essentially, these different types of neutrinos interact with other particles in different ways. They can even transform from one flavor to another, which is a phenomenon called neutrino oscillation.
Neutrino oscillation. That sounds wild. Is that something we can actually observe?
It is. Scientists have actually built detectors deep underground, shielded from cosmic rays and other interference, to catch these elusive neutrinos and study their properties. It's an incredibly challenging field, but the discoveries being made are shedding light on some of the most fundamental mysteries of the universe.
So we've got these tiny particles with 3 different flavors zipping through the cosmos and potentially playing a key role in the formation of black holes. This is way more complicated than I ever imagined.
And we're just scratching the surface. What's really fascinating is that these neutrino natal kicks, as they're called, might be much more subtle than the kicks from supernovae. And that brings us back to VFTS 243. It's a system where we can actually study the effects of these subtler kicks, or rather the lack thereof.
All right, you've officially piqued my curiosity. Let's delve deeper into these neutrino natal kicks and see what they can tell us about the universe.
Let's do it. So these neutrino natal kicks are fascinating because they offer like a glimpse into the subtle interplay of forces during a star's collapse. Remember, it's not a giant explosion pushing things around. It's these tiny particles carrying away energy and, crucially, momentum.
I'm trying to wrap my head around how something as small as a neutrino can actually kick a black hole. Even a little bit.
Yeah.
It seems like trying to move a boulder by blowing on it.
It does seem counterintuitive, doesn't it? But remember, we're talking about an unimaginable number of neutrinos released in a very short amount of time. It's like the butterfly effect on a cosmic scale. Each neutrino carries a tiny bit of momentum, but when billions upon billions are released, their combined effect can actually nudge the black hole.
Okay, I can see how it's possible, but I'm guessing these neutrino kicks are still pretty wimpy compared to the explosive kicks from a supernova.
Exactly. The kicks imparted by neutrinos are expected to be much smaller. And that's precisely why VFTS 243 is so important. It's a system where we can actually observe the effects of these subtle kicks, or rather the lack thereof.
Right, we talked about how the companion star's orbit is undisturbed, which points to a lack of a strong kick during the black hole's formation. But how do we know it's specifically these neutrino kicks, or the lack of them that we're seeing? Couldn't there be other explanations?
That's a great question, and the researchers addressed that by running different simulations. They modeled the black hole formation with and without strong natal kicks, like those you'd expect from a supernova.
So they were testing different scenarios to see which one best fit the observations.
Exactly. And the models that included strong natal kicks simply couldn't reproduce the observed orbit of the companion star in VFTS 243. The pieces of the cosmic puzzle, so to speak, only fit together if we account for these subtle neutrino kicks, or rather, the lack of strong kicks.
So it really is like a cosmic detective story. We've got our clues, our suspects, and our meticulous investigators running simulations to piece it all together.
That's a great analogy, and the implications of this cosmic investigation are pretty mind-boggling. If black holes can form silently and with minimal natal kicks, it means our current census of black holes in the universe might be drastically underestimated.
Wait, are you saying there could be way more black holes out there than we thought? Like a whole hidden population lurking in the shadows of the universe?
That's a very real possibility. Think about it. If black holes don't always announce their arrival with a brilliant supernova, we might be missing a huge chunk of them. They could be hiding in binary systems in the hearts of galaxies, or even wandering solo through interstellar space.
That's both exciting and a little spooky. It's like the universe just got a whole lot more mysterious and maybe a bit more dangerous.
Dangerous perhaps, but also incredibly intriguing. This discovery challenges our understanding of how these incredibly dense objects are created. We've always associated black hole formation with these cataclysmic explosions, but now we're seeing there might be a quieter, more subtle path.
It's like we're lifting a veil on a whole new aspect of the universe. And this brings us back to the title of the paper, Constraints on Neutrino Natal Kicks. By studying systems like VFTS 243, we're not just learning about black holes, but also gaining deeper insights into these elusive neutrinos themselves.
Absolutely. It's a beautiful example of how different areas of science can illuminate each other. By studying the motions of stars and black holes, we're gaining a better understanding of these tiny, almost undetectable particles that play a crucial role in shaping the universe.
It's incredible how interconnected everything is. And speaking of interconnectedness, there's another aspect of this research that I find particularly fascinating, the potential connection to dark matter.
Ah, yes. Dark matter, the ultimate cosmic mystery. It turns out that some theories of dark matter predict the existence of particles that, like neutrinos, interact very weakly with ordinary matter. And if these dark matter particles are out there, they might also be produced in the extreme environments of collapsing stars.
Hold on, so are you suggesting that these disappearing stars might not only be giving birth to black holes, but also spewing out dark matter particles?
It's certainly a tantalizing possibility. It's like these collapsing stars are acting as cosmic factories, churning out these elusive particles that hold the key to understanding some of the deepest mysteries of the universe.
That's mind-blowing. But I thought dark matter was, well, dark. How could we ever hope to detect it coming from these collapsing stars?
It's a huge challenge, but scientists are working on it. They're developing incredibly sensitive instruments and sophisticated techniques to try and catch these elusive particles. And while we haven't detected dark matter directly from these disappearing stars, yet it's an active area of research.
This is getting me really excited. So we're potentially talking about a two-for-one discovery here. Not only are we learning about a new way black holes can form, but we might also be on the verge of finally unlocking the secrets of dark matter.
It's certainly a possibility. And even if we don't find direct evidence of dark matter from these collapsing stars, the research is still incredibly valuable. It's pushing the boundaries of astrophysics and particle physics, prompting us to rethink our assumptions and explore new avenues of inquiry.
Okay, before my head explodes from all this cosmic awesomeness, can we try to sum up what we've learned so far?
Absolutely. Let's recap the key takeaways. Firstly, we've discovered that black holes can form without the dramatic supernova explosion we previously thought were essential. This opens up the possibility that there could be many more black holes lurking out there than we ever imagined.
Right, and the key to this silent formation process is those ghostly neutrinos carrying away energy and giving the black hole a subtle kick.
And because these neutrino kicks are so subtle, they leave the companion star's orbit undisturbed, which is exactly what we observe in VFTS 243. It's this lack of a strong kick that provided the crucial clue.
The cosmic billiards mystery. It all comes together beautifully.
And finally, we explored the tantalizing possibility that these disappearing stars might also be producing dark matter particles, potentially offering a new window into this mysterious substance that makes up the majority of the universe's mass.
So this research has not only rewritten our understanding of how black holes were born, but has also opened up a whole new realm of possibilities in the search for dark matter.
It's truly a paradigm shift, and it highlights the interconnectedness of everything in the universe, from the smallest subatomic particles to the most massive cosmic objects. But there's one more mind-bending twist to this story that we haven't discussed yet.
Oh, there's more. I'm on the edge of my seat.
Get ready, because this one delves into the very fabric of space and time.
Okay, you mentioned a mind-bending twist. I thought we'd already covered enough mind-bending material for one episode. What else is there?
Well, we've been talking about how these disappearing stars challenge our understanding of black hole formation and might even offer clues about dark matter. But there's another layer to this discovery that relates to something called gravitational waves.
Gravitational waves. Aren't those ripples in space-time caused by massive objects moving around?
Exactly. Think of it like dropping a pebble in a pond. The pebble creates ripples that spread outward. In a similar way, when massive objects like black holes accelerate or collide, they create ripples in the fabric of space-time.
I remember when scientists first detected gravitational waves a few years ago.
Yeah.
It was a huge deal. But how do these waves tie into the story of disappearing stars?
Well, if black holes are forming without supernovae, as this research suggests, it means they're not getting those powerful kicks that send them careening through space. They're more likely to stay in their original stellar neighborhoods.
So they're less like those cosmic pinballs we talked about earlier.
Exactly. And that means they might be more likely to interact with other black holes or neutron stars in their vicinity. And when those massive objects get close enough, they can start spiraling towards each other, eventually merging in a cataclysmic collision.
And those collisions would create gravitational waves.
Precisely. And those gravitational waves would carry information about the black holes that created them, including how they formed.
So by studying gravitational waves, we might be able to tell which black holes were born in a quiet collapse versus those formed in a supernova explosion.
That's the hope. It's like having a cosmic microphone listening in on the universe's most dramatic events. And the signals we're picking up are already challenging our assumptions.
Okay, I have to ask, if these disappearing stars are more common than we thought, and if they're leading to more black hole mergers, does that mean the universe is a lot noisier in terms of gravitational waves than we expected?
It's certainly possible. The early data from gravitational wave detectors suggests that black hole mergers are happening more frequently than some models predicted. And that might be because we're underestimating the number of black holes out there thanks to these quiet collapses.
This is absolutely incredible. We started with a single research paper about a seemingly quiet black hole in a distant galaxy, and we've ended up with a whole new perspective on the universe. Black holes, neutrinos, dark matter, and even gravitational waves.
It's a perfect example of how scientific discoveries often lead to unexpected connections and open up new avenues of exploration. What seemed like an isolated finding has actually created ripples across multiple fields of study.
It makes you wonder what other secrets the universe is hiding just waiting to be uncovered.
Indeed. And the best part is we're just getting started. With new telescopes, more sensitive detectors, and ever-advancing computer models, the next few decades are going to be a truly exciting time for astronomy and physics.
So to wrap things up, what's the one big takeaway you hope listeners will remember from this deep dive?
I think the key message is that the universe is full of surprises. We're constantly learning new things, challenging old assumptions, and expanding our understanding of the cosmos. This research reminds us that even the most seemingly empty regions of space might be teeming with hidden activity, from the subtle whispers of neutrinos to the dramatic collisions of black holes.
Well said. It's a humbling reminder that we still have so much to learn about the universe and our place within it. And it's an invitation to keep exploring, keep asking questions, and never stop being amazed by the wonders of the cosmos.
Exactly. There's a whole universe out there waiting to be discovered.
And on that note, we'll wrap up this deep dive into the mysteries of disappearing stars. Until next time, keep looking up and keep wondering.